Let us solve a simple Otto cycle problem. And this is a problem taken from chapter 7. Let's modify the problem a little bit. The compression ratio is given to be 8. Let's change it to 10. Okay, first thing first, we got to first draw the cycle on a TS diagram to understand the problem, to understand what is given to us. So before you start solving any problem, we draw the TS diagram, two constant volume lines. That's how an Otto cycle looks in a TS diagram. So these are constant volume lines. So 1 to 2 is the isentropic compression, and we know compression ratio is 10. This must be the state 1. So state 1, a lot of information supplied. Temperature at the end of combustion, so that must be the temperature here, 900 Kelvin. What else is known? That's it, and we have to find the highest pressure, amount of heat input, etc., etc. Okay, let's start by listing or evaluating temperature and pressure at each state. So state 1, what is supplied? Pressure is given, temperature is given. I'm just 20 degrees Celsius, I'm converting directly to Kelvin. And the volume at state 1 is given, 500 cc, which is 500 times 10 to the minus 6 meter cube, all in SI unit. We can use the ideal gas equation of state to find the specific volume and the mass, which we'll need later. And notice that specific volume remains constant from 2 to 3, which is given by this expression, and equals 0.84 approximately. So the mass, which is total volume by specific volume, density times volume, density is 1 over specific volume, is 5. Well, if we substitute the expression, 500 into 10 to the minus 6 meter cube, 0.84 meter cube per kg, which is a very small amount. So now that we know state 2 completely, we can find, state 1 completely, we can find state 2 because it's isentropic. And we also know the compression ratio. So if we go to state 2, let's first list what we know. We know that the specific volume is, or we can write volume 1 by 10 to us, because mass is same as m1. So the relationship being isentropic, to find the temperature, we are going to use equation 11, the isentropic relationship from the PG model, which is in table J. If you go to test, table J, or your textbook, it has the handout of all the different material models. So using the equation 11, we can write T2 over T1 can be written as V1 over V2 to the power K minus 1. And V1 over V2 is nothing but R, the compression ratio, the volumetric compression ratio. And that immediately gives us T2, which is equals T1 times R to the K minus 1, and substituting the values, we obtain T2 to be this, 736 Kelvin. And the pressure, which is, we can now evaluate, because again, PV equals RT, the ideal gas equation applied to equation state 2 will tell us that P must be equals RT over V. R is 287.287 for air. Temperature we just found, and we divide by the specific volume, which is 0.84. Remember, oh sorry, it's 0.084 because it's V1 over 10, and therefore pressure becomes equal to a very huge number, 2515 kPa. Let's go and evaluate what we are after, the cycle analysis based on as far as network or thermal efficiency, etc. are concerned. Again, we draw the cycle on the TS diagram. Again, I cannot emphasize how important it is to know how to quickly convert a cycle into a TS diagram. We know heat is added here. That's our Q in that takes place in the cycle. And this is where our Q out take place, right? And it's relatively easy to figure out Q in and Q out. So therefore, we will not calculate W in and W out because we know Q in is what? We have already developed the formula, but it's obvious. A closed volume of gas is taken from 2 to 3. So it's simply delta U because there is no work. And that's mCv T3 minus T2. So if we substitute the values, our mass is 5.9 into 10 to the minus 4. CV 0.718. Again, the value for CV and K and CP for air should be known, or you can find it from any PG table, from the tables module. And T3 is 900, that was given to us. And T2 we found to be 400. How much was the T2 we found? I think 738 Kelvin. And this turns out to be pretty small, 0.069 kilojoule. Likewise, we can find Q out. Q out will be, again, the higher minus the smaller one. mCv T4 is higher than T1. These are all positive numbers. So heat transfer in a closed process at constant volume, there is no work, therefore the formula becomes really simple. Again, this is the mass CV of 718, and T4, how much was the T4? I have that in front of me. It's about 358 Kelvin minus 290 Kelvin, and that turns out to be 0.0276. Well, we can go and find W net from there, but we got here. So Q in and Q out are correct. So therefore, W net, so this is the trick we are using, W net equal Q in, Q net basically, sorry. W net and Q net are equal, which is Q in minus Q out, which is equal to zero point 0.0417 kilojoule. So if you have to find the thermal efficiency of the cycle, of the Otto cycle, W net divided by Q in, and we can see that, show that it's about 60.2%. Let's just turn the problem slightly around and find some other numbers so that the definitions are clear. Notice W net has the unit of kilojoule. What does it mean? That means one cycle produces this much amount of work. So just suppose we have an 8-cylinder car or 8-cylinder device running at 3000 RPM. That's what your odometer in the car shows when you drive a car. So how can you convert that number into what is the power of the car? So this is from one cycle. So if you can multiply this by number of cycles, that will produce W dot net. And then if you multiply that by 8 cylinder, 8, then we'll get the total power of the cycle. In other words, so W net total equals 8 times W dot net, right? Which is 8 times, what is W dot net? N is the number of cycles times W net. Number of cycles per second, which is 8 times N by 2 W net. See if it makes sense. What is N? Number of revolution per second. By revolution, I mean, when you say 3000 RPM, what does it reflect? It is the number of revolution per minute of your crankshaft. And we know in a 4-stroke cycle, 2 revolutions makes 1 cycle. So number of cycles per second is number of revolution divided by 2. Number of revolution of crankshaft divided by 2. If it's a 2-stroke cycle, this 2 will not appear. So now the answer becomes 8. N is number of revolution per second, so that will be 3000 by 60, and this 2 is carried over, and W net is 0.0417, and so we get something like 8 times about 1.04 kilowatt, or it's something like 8.3 kilowatt. So it's a very small, very low power typically. So this is the academic problem, and normally this power should be about 10 times that. Okay, so we have determined the net power, we have determined the thermal efficiency, etc.